All right, hello and welcome. This is going to be our exponential and logarithmic functions test review homework help video. We'll go ahead and get started. I did problem number 1 in class. I think a good one to do would be 3 and 4 here. Number 3, I'm going to do this by making the bases match. It would be an easy problem to do with logarithms, but just want to show a different way. One way to do this is to recognize that 32 is a matching power to 8 if we use 2 as the base. So 32 can be expressed as 2 to the power of 5, and 8 can be expressed as 2 to the power of 3. Now this side over here still has to be raised to the power of negative n, and then we can use our product property to multiply these here. Now we've got 2 to the negative 5n equals 2 to the third, and the bases match on both sides, so we can effectively take log base 2 of both sides and get rid of them. Once they're gone, now we just have negative 5n equals 3. Divide both sides by negative 5, and we've got n equals negative 3/5. So we were able to get the answer. And one thing that's nice about this technique is that it doesn't require a calculator. If you were to do this with logarithms, you'd end up with log base 32 of 8 equals negative n, and we need a calculator to be able to evaluate this. Let's see. Number 4. 4 is an interesting one because of the linear equation that it creates. We're going to do this the same way. We're going to recognize that 64 and 16 can both be expressed as powers of the same base, and that base is 4. So 4 cubed equals 64, and 4 squared equals 16. So let's write them with those bases now. 4 cubed to the 2n minus 1, and 4 squared to the power of 3n plus 3. Our power to a power property states that we can now multiply these. You have an exponent raised to another exponent, you multiply the exponents, and now we've got 4 to the power of 6n minus 3 equals 4 to the power of 6n plus 6. The bases match on both sides, so we can get rid of them. Now we've got the equation 6n minus 3 equals 6n plus 6. If I subtract 6n from both sides here, I wind up with negative 3 equals 6. This tells us, because I was able to reach a contradiction using legal algebraic steps, that I have no solution. All of my variables cancel, and what I'm left with is a contradiction, negative 3 equals 6. So there's no number we can plug in for n to make these balance. All right, moving on. Use a calculator to sketch a graph of each function, show 3 points clearly, and state the domain range of each. Well, it says use a calculator. I'll do one with a calculator, one without, just to show the process. Number 5, I'll do it without a calculator. The first thing I'm going to do is fill in my horizontal asymptote. All right, so this is an exponential equation. Exponential equations always get horizontal asymptotes. They're always located at y equals k. In this situation, it's y equals negative 2. So I can dot in a horizontal line at negative 2. This is the line I know my function is going to approach. Let's see what else we can tell. I can tell that the a value equals 1/4, and that my b value is 4. All right, so my a value, sometimes called the starting value, it doesn't mean I'm starting up here at 1/4. It's not the same as y-intercept. It means that if this was the table that Alice was standing on, she's 1/4 of a foot tall above that table. So just 1/4 of a unit above this horizontal asymptote. It's barely different from the line itself. Let me do it in a different color. Like, let's do green. Just 1/4 of a unit above the line. Now the B value tells me how much she grows by each unit. So if she was a fourth of a unit tall, if she eats an ounce of cake, she should now be 1 unit tall, one unit above the table that she's standing on. We move one more over, that this point gets 4 times as tall. Now we're up at 2. She's 4. Now we multiply that by 4. She's 16 units tall. So 16 up from this level here is up to 14. And then we're off the graph. And on this side, we are flattening out to that horizontal asymptote very quickly. It's going to look basically like a horizontal line until we hit 0, and it shoots up this way. And here it's basically vertical going off the graph. Although this line is very steep, it's going to keep moving to the right. There's no wall that this line hits and it stops moving to the right. This arrow over here goes off towards negative infinity. That means that our domain here is all real numbers. X equals all real numbers. For range, there is a limit that we hit in terms of our y values. This arrow goes up to infinity, but the left-hand side of this arrow never crosses our horizontal asymptote. It never even reaches the horizontal asymptote. So there's a whole region of y values that this graph will never reach. And those are everything to -2 and below. So our range is always going to be y is greater than our k value. And in this case, it's y is greater than -2. So that's our range. And that's our domain. Let's try graphing number 6. We'll use the calculator to help us. Still, I'll fill in my horizontal asymptote because it's easy to do. I can see it's at -1. Just add in a dotted line at -1. We don't need a calculator to tell us that. So that's the line y equals -1. To get the rest of our points, we're going to plug this equation into TI-84 calculator and then use the table on the calculator to help us get some lattice points. All right, so I go to my y equals, clear on any equation that's there, and input the equation we've been given. 2 times 1/3 to the power of x, all of that minus 1. All right, so now I'm going to go second graph to look at the table. If it starts at a weird place, you might do second window and have your table start at a more normal place. I think -1's fine, counting up by 1s. And then I'm just going to look for the lattice points. I can see -2, 17 is a point on this graph. So -2, 17. I can also see -1, 5. I can also see 0, 1. 1, -1/3, and then we're really out of lattice points at that point. This is just going to flatten out to our horizontal asymptote. All right, so connect them up with an arrow, and we see this. It's almost a mirror image of the graph next to it because this one is exponential decay. We knew that it was going to be exponential decay because the b value is less than 1. All right, show 3 points clearly. If you want to be extra clear about that, you might label the points with their ordered pair, just like so. All right, moving on to our next page. You deposit $3,000 into an account that earns 12% annual interest. You leave this investment for 10 years. Find the final amount given the following circumstances. So simple interest. This is where we say, okay, 12% for 10 years. That's like basically getting 120% one time if you ignore compound interest. The formula for that is principal times 1 plus the rate times time. And so 3,000 times 1 plus the 0.12 times 10. Plug that into your calculator. Make sure to keep the parentheses in the right spot. 3,000 times parentheses 1 plus 0.12 times 10, close parentheses, gets $6,600. Compounded semi-annually. All right, so we've got compounding, but not continuous. Therefore, we're going to use this formula here. Final amount equals the principal times 1 plus the rate divided by compounding periods, all to the power of the number of compounding periods times the number of years. Let's plug in the values we have. A equals 3,000 times 1 plus that 12% is a decimal, 0.12. Semi-annually means that n equals 2. We're compounding twice a year for 10 years, so 2 times 10. Plug all that into my calculator. 3,000 times parentheses 1 plus 0.12 divided by 2 to the power of 20. And I get quite a bit more money. I get $9,621.41. Now the difference there between number 8 and number 9 is the effect of compound interest. Number 7 didn't have any compound interest. We only got 6,600. Number 8 did have the compounding interest, and we got a much bigger amount. Let's see if we can go even higher by compounding monthly. So that's going to be 3,000 times 1 plus 0.12 divided by 12 to the power of 12 times 10. So 3,000 times 1.01 to the power of 120. We get $9,901.16. So we get more money than compounded semi-annually by compounding monthly. Not a huge amount. Let's see if we can stretch it a little bit more by doing compounding continuously. This is a different formula. A equals P e to the RT. So 3,000 times e to the rate times time. So 3,000 times e to get e, do second divide on your calculator to the power of 1.2, 9,960. So we do squeeze out just a few more dollars by doing the compounding continuously. Not a ton, but not nothing. 9,960.35 is our final answer for that one there. All right. I take out a loan for $200, annual interest rate of 16% compounding quarterly. How long until I'll no longer be able to repay the loan with the $800 I have in cash? So we want to know when this number here, 200 times 1 plus 0.16 divided by 4 to the power of 4t. Why don't we calculate when it equals 800, and then we'll round up to the nearest quarter. All right, step 1, I'm going to divide both sides by 200. And I'm going to combine what's inside that parentheses to be 1.04. So now I've got 4 equals 1.04 to the power of 4t. At this point, I have to rearrange it into a logarithm. So the base of the exponent becomes the base of the log. So log of 1.04 of 4 equals 4t. Divide both sides by 4, and this is what I want to plug into the calculator. So with the newer calculator, I can just plug this in directly, basically. I have to hit math, and then scroll up to this log base option, and I can edit the base directly to be 1.04. 4 here, and then let's divide that whole thing by 4. All right, 8.83. If I've got an older calculator, I have to use a change of base formula, so I want to do log of 4 divided by log of 1.04. This is going to give me the top part of that fraction, divide that by 4, and we get the same number, 8.83 years. So 8.83 years. So when it compounded at 8.75 years, we did have enough cash. It's at 9 years is where it exceeds the $800 in cash that I have. We have to wait another compounding period. All right, solving equations here. Round your answer to the nearest 10,000th. This is a straightforward isolate n situation. We'll have to use a logarithm at one point to do so because our variable is inside the exponent. All right, so to get free our variable, we have to rearrange this into a logarithm. So log base 17 of 10.4 equals n minus 4. Let's just plug this into our calculators. I'm doing log of 10.4 divided by log of 17. I get an answer of 0.82. Dot, dot, dot. Subtract 4 from both sides. And we'll get, we need to round this to the nearest 10,000, so negative 3.1734. So that's our tens, hundredths, thousandths, 10,000ths. All right, all of these are about that same level of difficulty. Let's move on to 16 through 19. We need to rearrange these into exponential form now to solve for our variable. Let's see which one looks the most difficult. I guess 16 looks somewhat challenging. I want to get the logarithm by itself, so I divide both sides by -9. I get log base 4 of negative 4k equals -1. Rearrange this now into exponential form. 4 to the 1 equals -4k. Divide both sides by -4. I get -1 equals k. Just check this is going. -1 equals k there. Give me -1/6. I think I missed something. Let's see, I divide both sides by -9. That gives me -1. 4 to the power of -1. I needed to simplify that. I lost a negative there, but the answer didn't look right, so I need to go back and check. So 4 to the -1 is 1 over 4 equals -4k. Now when I divide that by -4, when you divide a fraction by a number, you could just multiply that number to the bottom of the fraction. This is 1 over, make it -1 over 16 equals k. Let's see, is there another one that we should do? I guess 18. Let's add 5 to both sides. Log base 3 of -5n equals 0. Rearrange this into exponential form. 3 to the power of 0 equals -5n. 3 to the power of 0 is equal to 1. So this is now 1 equals -5n. Divide both sides by -5. N equals -1/5 for 18. All right, moving on. All right, I need to condense these into a single logarithm. Although it's not stated, I don't need to simplify my exponents. So for number 20, for example, I can rewrite this just as log base 8 of 10 to the 12th, and then just leave that as 10 to the 12th. I don't have to write that out. Minus log base 8 of 11 to the 4th. Now this here equals log base 8 of 10 to the 12th divided by 11 to the 4th. And we've got it down to a single logarithm. Let's not worry about simplifying the argument any further than this. I don't think that it can be simplified very easily. It's a very convenient number. $22 is kind of an interesting one. This is going to become log of 8 to the 3rd. But how do I deal with this? Well, I could say that's the same as 1/3 log of 3. Log of 3 divided by 3 is the same as taking log 3 and multiplying it by 1/3. Now this can become log of 3 to the power of 1/3, which can become log to the cubed root of 3. I know these are being added, so we'll just do log of 8 to the 3rd cubed root of 3. Call that good. $24 and $25 are basically testing your calculator skills. If you can plug this in correctly, so log base 6 of 5.6. Let's just show that change of base formula one more time. You got to switch the numbers around and do a log for each one and divide the two. So log of 5.6 divided by log of 6. This is the same as log base 6 of 5.6. And we get 0.96. Nearest thousandth. So that's hundredths. One more decimal place, and 6, 1. All right, here we need to solve these equations. I can see that I've got two logarithms with the same base, so I know automatically I want to condense that into a single logarithm. For 26, this is going to become log base 3 of x plus 4 divided by x. The subtraction becomes division, equals 1. And once you have it condensed to a single logarithm, rearrange it into exponential forms. This becomes 3 to the power of 1 equals x plus 4 over x. And now we just have to solve this. Maybe I'll multiply x to both sides. Times x times x. Now we've got 3x equals x plus 4 minus x minus x. 2x equals 4, divided by 2, divided by 2. X equals 2. Let's see if I see another challenging one. Here, maybe number 29. We'll give you some problems. So let's see, log base 2 of 5 minus log base 2 of that. I can subtract them, right, as a single logarithm. Log base 2 of 5 over x minus 6 equals 5. Now we got to rearrange it into exponential form. So this becomes 2 to the 5th equals 5 over x minus 6. 2 to the 5th is 32. See, I think I'll multiply x minus 6 to both sides to cancel it out on this side. So those cancel. Now I've got 32x minus 6 times 32. 190, no, not 96, 192 equals 5. Add 192. Divide both sides by 32. $6.15625. Let's see if that's a convenient fraction. No, we'll just leave it like that. I wonder how they leave the answer in the answer key for 29. Oh, they just leave it as the fraction, 197 over 32. All right, so number 30 and 31 say identify the domain and range of each. These are logarithmic functions, so we know that their range is going to be all real numbers, but the domain is going to be restricted. The key to figuring out the domain is to take the argument and just say that the 3x plus 3 must be greater than 0, because we cannot take the log of a negative number. Therefore, the argument must be greater than 0. And then just solve. So I get 3x is greater than negative 3. Therefore, our domain is that x is greater than negative 1. The range is going to be all real numbers. Y equals all real numbers. All right, same thing over here. Just take that argument, say that it must be greater than 0, and solve. All right, finding inverses. The very first step of finding an inverse is always the same. We just need to swap x and y. So to find an inverse, you got to swap x and y. So this becomes x equals 6. And it's the log of 1/2 power of x, or the x now is a y. Now we want to isolate y. So I'm going to do that by potentially dividing both sides by 6. I have x over 6 equals log base 1/2 of y. Rearrange this. This now becomes 1/2 to the power of x over 6 equals y. I think we can just leave our answer like that. 32. Yep. Well, they distribute the x to the 6th to just the bottom of this fraction. Well, technically to the top two, but 1 to the power of anything. It's just 1. So that's why there's a slight discrepancy with this answer and the answer key. Be able to do both. Let's try 34 and 35. I swap my variables here. I got x equals 3 log of 1/3 equals y. Divide both sides by 3. X over 3 equals log base 1/3 of y. Now we've got 1/3 to the x over 3 equals y. And I'm sure the answer key's probably got it as 1 over 3 to the x over 3 equals y. Both are fine in my book, but be able to do either. Let's look at 35. Step 1, swap x and y. Step 2, isolate y. So this is going to become 10 to the power of x equals y to the 4th. Notice, although the base of this logarithm wasn't written, it was a 10. That's always the default base of a logarithm. To get rid of this 4, I could raise both sides to the power of 1/4, which is what I'll do. You could also take a 4th root. And so now we've got 10 to the power of x over 4, right? Exponent to an exponent, we get to multiply them, equals y. All right, and that is right. Let's see, 36, looking a little bit challenging. X equals 1 over 4 to the 1 plus y. I'm going to make this x equals 4 to the negative 1 minus y. I flip the signs, I can bring it back up to the numerator. Bring this over here. Log base 4 of x equals negative 1 minus y. Add 1, divide both sides by negative 1. And we get negative log base 4 of x minus 1. Interesting. They went log base 1/4 of 4x. Let's see. I'm thinking this is just equivalent to the answer in the answer key. Let me just double check. I don't see any mistakes. 4x, negative 1. Yeah, the 1. By that by negative 1. Yeah. So this must be an equivalent form for 36. I'm thinking they took the way that the other answer was gotten was by taking this exponent, writing it out in front, making it 1/4 to the power of 1 plus x, and then rearranging it from there. But all right, let's move on to our last two. All right, domain and range, then use the graph calculator to help you sketch the graph. So for the range, no, for the domain, we know that x minus 1 must be greater than 0. Therefore, if I add 1 to both sides, I get that x must be greater than 1. That is our domain. That also tells us where the vertical asymptote is. There should be a vertical asymptote at x equals 1. All right, to graph this, it says we can use our graphing calculator, so let's just do that. I'm just going to plug it in and look for easy to plot points. So use a change of base formula to plug this in just to show that. And we'll now look at the table to try to find our ordered pairs. So 1 is our first error message, so that's lending support to the fact that 1 is our vertical asymptote. I see the point 2, 2, so let me add that to my drawing. 2, 2, 3, 3, and 5, 4. 3, 3, 5, 4. I think by the time we reach 5, we're off the graph. See if that's accurate. Well, okay, so 9 over, 5 up. Yep, just off the graph for that last point. So let's connect the dots. And one thing is make sure the ends go all the way off the graph. So on this side, this end goes all the way off over here, but over here, on the left-hand side of this graph, it needs to approach our vertical asymptote, not cross it, but just go straight down with it. Mine crosses a little bit. It wasn't supposed to do that. It's supposed to just go flat to this line and go all the way off the graph. All right, I think that's a pretty good review of this unit. Come to class with questions, and best of luck on the test.